my God. Check out this faucet. So much water. I'm in the middle of the Ciencia Desert. Now, where exactly is the Ciencia Desert? My garage. And why do I have a mock-up of a desert in my garage? Well, because I want to definitively answer a very consequential question. By combining high voltage with overnight fog, can some desert water shortages become a thing of the past? To help me answer that, I've spent the past 2 months designing a one-of-a-kind fog condenser that is relatively portable, solar rechargeable, and converts fog into water within seconds. It's a strange-looking design, and to better understand this mission, we need to go back to earlier this year when I built this. This video is sponsored by Saley. Righto, let's talk fog nets. Many coastal deserts experience fog at night and the early morning hours. For hundreds, if not thousands of years, cultures in those areas have been using fog nets to collect water for their daily needs. The nets act as a nucleation point for fog to condense onto, creating liquid water at the bottom of the net. However, fog nets are purely passive devices. They function merely off the grace of fog droplets bumping into them on a foggy night. If there's zero wind, the nets aren't very effective. Because of their passive nature, fog nets of all designs typically capture no more than 2% of the water that passes by them. Oh, that's terrible no matter how you slice it, and it leaves a ton of room for improvement. That's why earlier this year I decided to try an active approach to collecting fog, and design this. An electrostatic fog condenser. It was portable and using 20,000 volts produced 9 mils of water per minute. At the end of the video, I talked about next steps. I want to refine this further into a larger system and then test it out in the Atacama Desert in Chile. And if I was going to upscale this condenser for real-world tests, it gave me the opportunity to improve the design in the process. So let's talk about the past design and where it could use some improvements. First, height. At 8 inches in height and a single collection surface, it only captures fog right at the 8-inch elevation band. Increasing the collection surfaces to cover more elevation bands means collecting more water. Second, power. The addition of a 12-volt solar panel would allow for automatic recharging during the day, and boosting the power would allow for a much larger system. Lastly, shape. The previous design is great with zero wind, but not so much with light wind. So I need a geometric layout which is adjustable and captures fog in low wind situations. Taking the good from the original design and incorporating these new improvements, I had 2 ideas for a new physical layout. Structure option 1, a double-layered ionic condenser built in the shape of a large circle, 1 powered stake and multiple support stakes. Being circular, it guarantees that even in moderately windy situations, all fog will pass by a condensing site twice. Structure option 2, a double-layered ionic condenser built into the shape of either an X or a chevron, 1 central powered stake with all electrodes extending out from the middle towards each support stake. This also guarantees all fog passes by a condensing site twice. Ultimately, I went with option 2 in the shape of an adjustable chevron. Adjustable so you can change its angle for each angle of incoming wind. Feeling really inspired and certain that this would be an easy build, I went ahead and booked a flight to Peru for real-world tests. What do you think, buddy? We gonna find anything good? It's booked. I'm headed to Peru in 2 weeks. Wow, so I only have 2 weeks to build this. Okay. Now, Peru is not the only place this could be tested. Chile and Namibia also have coastal deserts with long-lasting nighttime fog. Regardless, travel is travel, and that means you'll need cell service either way, and that's where this video's sponsor, Saley, comes in clutch. Most cell phone carriers will provide you service while you travel internationally, but it's basically like signing up for a highway robbery, and even then, there's no guarantee you'll get good service. When I traveled to Egypt, it was $10 a day for 2 gigs of service. Here's a way around that. Saley is a phone app which helps you stay connected in over 200 places around the world. It provides you an eSIM, essentially a digital ID for your phone, allowing your phone to work normally in each of those locations. Without this, your phone's SIM card needs to be replaced physically in every country you visit, or you need to pay for expensive roaming fees through your cell provider. And here's how Saley works. Just choose either a global or regional data plan, install on your phone a single time before traveling, and you're set. You'll have internet wherever you go without expensive roaming fees. And really, that's just the main cake. The toppings include security features such as changing your virtual location, blocking malicious online ads, and dedicated web protection. All Saley eSIM plans are compatible with Apple or Android devices, and they have 24/7 support. Pretty sweet deal, and when I travel to various deserts for field tests, I will be using it. You can get an exclusive 15% discount on Saley eSIM data plans by downloading the app and using code PLASMA at checkout, or you can click the link down below. The first version of this condenser used a garden stake format, so I expanded upon that layout with one central powered stake with built-in hinges positioned 45 degrees apart. This central stake will act as the brain and energy source, with its hinges connected to independent wings, each with dual condensers powered in parallel. The wings slope downward at 4 degrees, allowing water to drip off of these extensions, and with their hinge attachments, both wings can be placed in various positions. I always use Onshape for all of my designs, and I'll leave a link down below for you to try it for free. So it's the next day, and after a bit of glue to bond the two pieces together, the most important part of the project is complete. This is the central stake. It'll hold all the electronics needed for the condenser to operate, and you'll notice pitting this up against the version 1 from about 9 months ago, slight size difference, because this will need to handle about 3 to 4 times the power output and manage a way larger system. Just like the original, rechargeable lithium batteries are on the back side, driving circuitry on the front, high voltage transformers in the middle to convert the battery voltage into high voltage AC, and then on the top are voltage multipliers. The original stake had 3 stages, the new one will have 4, while the rest of the parts for the condenser are printing out, as I'm sure you can hear right now. I'm gonna do the fun part, which is build out the powered stake. I started by modeling up a custom high voltage transformer. This was then sent over to my Formlabs 4 printer, which is a liquid resin printer and such a wonderful tool to have. It prints an entire layer at once and gradually turns liquid resin into solid plastic. Whoopsies! As with all resin printers, it then needed an alcohol bath to remove remaining resin and make it safe to handle. Cool process to watch, honestly. Afterwards, some additional UV curing strengthened and fixated the structure. Thank you to Joel from 3D Printing Nerd for setting me up with this, and to Formlabs for simply being awesome. Then the tedious part, winding the form carefully with 500 feet of wire and assembling the actual transformer. After winding the secondary, I added 10 turns for the primary, which was just a totally arbitrary number just for testing, but regardless, this is the heart of the entire condenser. Now, I didn't do any calculations, so I need to test this and maybe find the right driver for it. My immediate thought was to use the 555 driver from my custom high voltage transformer video. Now, that transformer ran at 11 kilohertz because of its massive size, but this flyback is much smaller, so it would need a much higher frequency. Randomly, I set it for 30 kilohertz. Random stab in the dark, and that's a 1/4 inch gap. Oh, I should have guessed those wires would melt. After a few adjustments, I found that 17.5 kilohertz was the sweet spot to drive this transformer. Yes! Now that is what I've been going for. That is 1/2 inch. With the transformer knocked out, I moved on to building the voltage multiplier. This component is responsible for creating the wildly high DC voltages this project needs. So I've got all the parts built for the powered stake, the driving circuit, the transformer, and the multiplier, but I have a problem. As awesome and powerful as these 555 driving circuits are, they have a tendency to get really, really hot, even if you have a huge ass heat sink attached to the MOSFET like I do here. This gets like hot to the touch within about 2 minutes. And I need this powered stake to be operational for hours at a time. So I need to find a way around this. Of course, the first thought would be, why not use a ZVS circuit? They are powerhouses that don't get that hot. Well, they can also be really difficult to dim the power on. And for testing purposes, I need more than on-off. I need adjustable power. So I did some digging and found a new, highly efficient type of MOSFET that has 1/10 the typical on resistance, meaning no heat. With the new MOSFET, I built a customized driving circuit with some clear perf board I printed, because hell, why not? And managed to make it smaller as well, just small enough to sit perfectly onto the stake. With the circuit fitting well, transformer slides right in, and the multiplier perfectly up top. Now just to connect everything up and fill it with resin. You've seen this flyback secondary I wound, but eventually I moved on to a 4-section, then 5-section winding to reduce the risk of high voltage failure. Okay, everything's connected up except for this connection right here going to the main transformer so that I can test out the driving circuit. Ah, beautiful. Okay, and duty cycles adjustable, frequency is adjustable. We are golden. And it's come that time when everything goes wrong. First tests. For this test, I've taken the electrical ground of the multiplier and ran it up to about a 1-inch gap in front of the high voltage out. Now I figure I'll start small. 1-inch gap should be child's play. 50 kilovolts should have no problem jumping that gap. So that's gonna light up with sparks. 3, 2, 1. The hell? Shocker, turns out the 1-inch gap was too short for 50 kV. It was quietly shorting out continuously through the air. So I doubled the gap. Oh, that's juicy. That was a 2-inch gap. Oh, that's a bad noise. So here's the issue. Whew, yep, circuit board's not happy. In fact, I just broke it. Clearly, this circuit was not going to work. At these DC voltages and power levels, parasitic static charges flying off of every component becomes a real issue. Couple that with the static sensitive IC chips only inches away, and you get glitchy behavior. Big shocker. It was at this moment I realized I would not be making my 2-week deadline for Peru. Simply pushing back the flight a couple of weeks also wouldn't work since the predictable fog season in Peru slows down mid-October. But where I test this condenser matters less than simply testing it. So I searched for other possible driving circuits, and ironically, I settled on my own version of a ZVS driver that actually can handle reduced power. It worked really well, and as is typical with ZVS drivers, it output a beautiful AC waveform at 16 kHz, and powering another transformer at least 10 kilovolts of gorgeous plasma. After multiple tests, I found a compact dimmer capable of handling the power load, providing a PWM style of power dimming. As the dimmer switch is rotated, its ratio of on-off changes, which you can clearly see here. Starting small. Ooh, that's juicy, yes. Yep, this should solve the problem. Sliding this new driving circuit into place and rewiring the flyback primary to accept a push-pull AC signal, oof, I was getting all warm and tingly inside. Well, after a bit of work, new driving circuit, ZVS powered, no sensitive microchips, and a hell of a lot more power. Check this out. 3, 2, 1. Fully adjustable. And if you current limit the output like I have in this shot, you're treated with this beauty. Still fully adjustable. And watch what happens when I go to full power. Pitting this up against the powered stake from the original Fog Condenser. Oh God, such a little cutie. Well, it took long enough, but I have officially made the world's most dangerous garden stake. All delicious 50,000 volts. Whew, will not only condense fog, but also kill everything in your garden if you used it for that purpose. Now, this powered stake provides all the power for the condenser. The rest of the build, easy peasy plasma squeezy. Assembling the rest of this condenser would literally follow like 95% of the same instructions as an actual desert deployment. And at this point, it was painfully obvious that I had missed my 2-week window for Peru. So I figured, after a bit of bean water, if I can't go to a desert, why not bring a desert to me? This meant grabbing a few desert-adapted plants, close to 500 pounds of sand, and saying goodbye to any chance of a clean filming studio ever again. Convincing myself that I'm not that strange, I got to work building a desert in my garage. I never built a desert before, but that was fun. As for the condenser, it has one central powered stake followed by 2 support stakes and 2 inner end caps. 4 square tubes act as both the high voltage grounds and a structural spine. Kicking off the assembly, the central stake and end caps connect to form a 270-degree hinge, then each pair of square tubes is inserted into a support stake and bolted into place. Next, those tubes are linked up to the powered stake and also bolted into place. The process is repeated for the other side, and the entire structure at that point is pretty much assembled. The idea behind this design was ease of assembly and physical stability, if deployed in a sandy situation where the stakes can be inserted into the sand. However, in my concrete garage, the stakes don't have that stability, so buckets of sand will have to work for now, with 1 bucket for each of the 3 stakes. Lastly, it's just a matter of distributing the high voltage from the central stake to the rest of the condenser. And with that, I officially have a desert fog condenser in my garage. Totally normal person things. Assembly took about 5 to 10 minutes. If I was out in the field and not filming, it could probably be assembled in about 5 minutes, so it's fairly simple. Now I tested all the parts individually and they work flawlessly, but now it's all together and variables change, so I'm gonna be praying a little bit, hoping, and expecting the science to pan out, because it's time to test it. Here's to hoping for water with the flip of a switch. Just a little turnsy. Ooh, yeah, that sounds really angry. Oh. But I can feel ionic thrust being produced underneath each segment. That means fundamentally it's working. Awesome. A little more power. Super angry. It works. At least the physics. So far I was staying cool to the touch, and that buzzing noise was kind of like an animal deterrent. Anyways, next I tried 3/4 power. A lot louder, okay, and a lot more airflow. I can feel it. It's very obvious that this is pulling in air. Now, just like the tests I did with the dimmer switch and the high voltage transformer, full power is completely silent. Same case here. Here's full power. Oh, yeah, baby. The airflow is consistent at just over 1 meter a second, which should be perfect for circulating foggy air. To produce fog, I use dry ice because dry ice fog is the closest thing to natural fog. Oh yeah, that fog is drawn right in. Right in. It's already condensing, all right, along the main pipe. There's already condensation. Oh, that's beautiful. That's working really well. Pure water from fog, no wind required. So that first test showed a lot of promise. That was technically only like 1/4 or 1/8 of the entire condenser. But I want to test this. That means testing all 8 linear feet. Technically 16 linear feet since it's double stacked. That meant really upping my dry ice game with an industrial fog machine used for weddings. Suiting, because I'll be marrying the crap out of fog droplets. Giving it a couple minutes to fill my desert, I realized the concrete floor was going to cause an issue. Normally the stakes would be inserted about 12 inches into the ground, so the entire device would sit lower. Since the stakes can't be stabbed into the concrete, the device sat unnaturally high, too high for the artificial fog, so I raised the fog machine for the sake of these tests. This is just annihilating the fog. It's just getting sucked right in, converted directly into water. Oh my God. Check out this faucet. Beautiful. So much water. That is liquid water. As for the other wing, it performed equally as well, if not better. I mean, you can see right here multiple streams of water dripping down. It's an actual faucet. Hold on, check this out. It works, oh my God, it works so well. And yeah, I'm using unnaturally dense fog, but I don't know, man, I'm kind of new to the whole desert in a garage thing. As for the water, as for the actual numbers, oh my God, let's talk numbers. They are wild. So the original fog condenser consumed 40 watts of power and produced 9 milliliters of water per minute, giving it a 14 milliliter per watt hour efficiency. This improved condenser consumes 120 watts of energy and produces 42 milliliters of water per minute, giving it an efficiency of 21 milliliters per watt hour. It's 50% more efficient, captures fog from a wider elevation band, and it's solar rechargeable. Yeah, I didn't show you that part yet. It was tricky, but I wired together a portable solar panel and a 3S LiPo charger, then 3D printed a platform for them. Together, they work to charge the battery during every sunny day. Considering fog only happens at night and charging only happens during the day, it's a good cycle to take advantage of. I still haven't figured out a fog-activated switch, so for the time being, this device needs to be turned on manually at night. I imagine something like a Bluetooth-activated switch might be a good workaround. As for the adjustable chevron shape, this increases effectiveness in situations with predictable wind patterns by allowing windy fog to pass over a condenser site twice. Look, for the time being, I think this shows tremendous promise for agriculture and potable water, and at the very least, it's a giant step towards a more commercialized electrostatic fog condenser. Looks like I need to book another flight. Let me know your thoughts in the comments down below and where you think the field test should be. I've gotten offers from viewers in Peru, Namibia, and Saudi Arabia. Thank you so much for watching, and you stay classy. I'm gonna build a sandcastle now.